Hey guys, I'm John and welcome to Respect Your Intellect. Quantum entanglement is perhaps the most mysterious of the quantum effects, and in this video we'll talk about what it is, how it works, and what we know and don't know about it. Don't forget to hit the like and subscribe buttons, and let's get started. If you've been following some of my earlier videos that brush on the topic of quantum effects, you should already be aware of the wave-particle duality of particles in the quantum world, where particles travel like waves and collapse to particles when they interact with the outside world. If you're not sure how this all works yet, I recommend you check out my double slit experiment playlist, where I have a video on the double slit experiment and the quantum eraser experiment that show how particles behave. To start off, let's talk about what the difference is between simple particles and quantum entangled particles. Simple particles, as you should already be aware, all travel as waves, just like waves in a pond. This wave contains all the probabilities of all the possible locations that this particle could be found on the wave. It's when we make a measurement to observe the particle that the wave will collapse, and the particle will choose a single location and path. To put it simply, particles never resolve their definite locations, unless it's made absolutely necessary by an interaction. Entangled particles are essentially two simple particles that spatially overlapped while they were traveling as waves, and somehow become connected to each other. Since their waves affected each other during the overlap, they can no longer be described independently of each other and therefore become entangled. At this point, quantum mechanics requires us to use a combined wave function that encompasses all the states of both particles at the same time in order to accurately describe the entangled system. Once particles are entangled, at any moment and regardless of the distance between them, any interaction of one of the entangled particles will instantly collapse the other. This happens faster than the speed of light, and even back in time, as was shown in my quantum eraser video. So if we entangle particles and make sure not to measure them or interact with them in any way, to maintain their uncertainty and superposition of all their states, we can then separate them however we like and only later collapse them. Another thing that's important to know is that there is a clear correlation between the particles. When we generate an entangled pair in such a way that the total spin is known to be zero, then a measurement that yields a clockwise spin on one particle guarantees that the other is spinning counterclockwise. To this date, quantum entanglement and this correlation has been demonstrated literally countless times with photons, electrons, molecules, and even small diamonds. There's a principle in classical physics that states that the universe keeps existing independently of the mind of the observer. In other words, the universe continues to exist and function regardless if we're looking at it or not. This is called realism, and Einstein was a big believer in this idea. The other idea that Einstein really believed in was locality. This is the idea that things in the universe can only affect their direct neighbors and propagate outwards that way at a speed limited to the speed of light. However, even if this is something that we often take for granted, quantum mechanics makes us question whether we should reject even this basic premise. Quantum entanglement demonstrates violations of locality because it's an effect that happens faster than light, and also violates causality because the effect can precede the cause and seemingly rewrite the past. One good example of this is when we use gravitational lensing to look at distant galaxies that sent out light billions of years ago. Gravitational lensing happens when the photons that are on a straight path toward us are bent around a massive object between us and the object we're looking at. This makes the photons bend before they resume their straight path towards us. If we use a single telescope to look at this, it's not known which path the photon took around the massive object, and we get an interference pattern, showing that the photons traveled as waves. However, when an astronomer on Earth today uses two telescopes to determine exactly which path the photons took, the interference pattern is destroyed, showing that the particles did not travel as waves. So how we choose to act today influences particles that left billions of years ago, showing that our present decisions can affect the past, and that time plays no role in the results of this experiment. Niels Bohr and Albert Einstein had a series of public disputes about quantum mechanics, which are remembered because of their incredible importance to the philosophy of science. These disputes called attention to an element of quantum theory called quantum non-locality, and it's central to our modern understanding of the physical world. This quantum non-locality contradicts the assumptions of local realism that's found in classical physics and that we're all already naturally familiar with. So for the disputes, on the side of local realism was Einstein, and on the side of quantum non-locality was Bohr. Einstein called quantum entanglement spooky action at a distance, and was defending local realism by using a theory that states that everything needed to be determined at the moment of creation, since information can't travel between the particles faster than the speed of light. This is the hidden variables theory, and it simply states that there are hidden variables in quantum mechanics that are encoded at the moment of creation that we're simply not aware of. An example of this is having two boxes with gloves in it. One box would have the left glove and the other would have the right glove. Even if you don't know which one contains which, it wouldn't matter how much distance there is between the boxes, because as soon as you would open one, you'd also know what the other box contains. Originally, Einstein was not the only one to think that this hidden variables theory was the only way out of this paradox of faster than light communication between the particles. There were many scientists that believed the same thing. Bohr, on the other hand, was simply saying that it's futile to try and apply realism to unobserved parts of the universe, and that without interactions, everything was existing as a fuzzy mixture of all their possible states simultaneously. In order to settle the dispute of whether there were hidden variables encoded at the moment of creation, we needed to test the predictions made by both Einstein and Bohr. There's a theorem called Bell's theorem that was devised specifically to determine whether or not the entangled particles communicated information faster than the speed of light. Bell came up with a way of testing this by creating Bell's inequalities that should be satisfied if the local hidden variables theory was correct, but many different experiments showed that it's not satisfied. We do this by using our measuring devices that affect the particles at the time of measurement. What happens is that whenever we measure the spin vertically, we get an up or down result, and whenever we measure the spin horizontally, we get a left or right result. Any other orientation in between is a fraction of probability that depends on the angle between the vertical and horizontal positions. I won't go into too much mathematical details here, but what we would expect to see if hidden variables were true is that we'd get a correlation between the particles at the very least more than 55% of the time. What we actually see is that the correlation is exactly 50% of the time. So the hidden variables theory can't be true. The theorem goes on to state that there is no theory of local hidden variables that can account for all the predictions of quantum mechanics. So the hidden variables theory doesn't work, and the idea of particles having local hidden variables is shown to be false. In order to explain what's happening with entanglement, the property that usually has to take the fall is the idea of locality that Einstein was defending. This idea that no physical effect can travel faster than light. Because of these results, the consensus today is that Bohr was victorious in this debate, and the spin information is not encoded in the particle at the moment of creation. Now, as to how that information is communicated to the other particle of the entangled pair is still the mystery we're trying to figure out today. Different interpretations are attempting to explain this in different ways, but we don't have a clear answer right now. Since the measurement always yields a 50% possibility of measuring the spin in one direction or the other, it can't really be used to transmit information faster than light either. For example, if Alice has a particle and Bob has the other particle of the entangled pair, there is nothing that Alice can do that could send a definite and chosen value of, say, 0 or 1 to Bob without breaking the entanglement. Anything you do to force a 0 or 1 will break the entanglement, and Bob's value will have no correlation with Alice. And without forcing a value, you're always sending random data that Bob can't make sense of. It's only when you can physically compare notes that you realize that you have exact opposite values, and this physical comparison is still within the constraints of the speed of light. So as it stands today, we would still at the very least be limited to the speed of light to transfer the information about particles and compare notes to realize the correlation of opposite values on both sides. Another thing that's worth mentioning at this point is that we can't really guarantee that the transmission of the spin direction from one entangled partner to the other is instantaneous. It certainly looks instantaneous as far as we can tell up to now, but all we can say with absolute certainty is that it's at least 10,000 times faster than the speed of light. As we continue to test this over greater and greater distances, we might become more and more certain that the transmission is essentially instantaneous. So is entanglement something we find in nature, or is it something we have to always make in a lab? Well, in nature we do find entanglement in many different places. One example is the electrons of every atom that has more than one electron in their shell, due to their proximity to each other. It's also suggested that photosynthesis, which is the chemical reaction that transforms light into energy for plants, involves entanglement for the transfer between the light harvesting complexes and the photosynthetic reaction centers, where the kinetic energy is harvested in the form of chemical energy. Without such a process involving entanglement, we can't explain the efficient conversion of optical energy into chemical energy. There were experiments performed with femtosecond spectroscopy, which is an area of chemistry that studies chemical reactions on extremely short timescales, like atoms and molecules rearranging themselves, that were able to show results that support this theory of photosynthesis using entanglement. As for methods for creating a pair of entangled particles, it's not always the easiest thing to do, but we can do it. With photons, we can create an entangled pair by using a crystal that splits photons into two identical photons of half the energy of the original. This method is called spontaneous parametric down conversion, or SPDC for short. The best example of this being used is in the quantum eraser experiment, of which I have a video that you can check out. We can also create entanglement for other particles that never directly interacted by using entanglement swapping, which is actually a form of quantum teleportation that we'll cover soon in another video. Another thing we can do is to entangle independently prepared particles by spatially overlapping their wave functions, at least partially. Once they overlap, they affect each other's possible states and become entangled because they can no longer be described as independent particles. Alright, but now how can we use entanglement to our advantage? Well, even though pretty much everyone agrees that entanglement can't be used to transmit information faster than the speed of light, we're not getting discouraged, and entanglement in communication and computing are very active areas of research today. In 2014, we took the first pictures of objects using photons that never interacted with the subject, but were instead entangled with other particles that did interact with the subject. This new quantum imaging technique could prove useful where low-light imaging is important, like biological or medical imaging. Also, in 2016, many companies successfully created quantum computers and started allowing its users to openly experiment with concepts of quantum mechanics, including quantum entanglement. So, with all this research happening and all these possibilities at our disposal, there's good reason to be hopeful for very significant advancements in the future. It may be that we never find a way to use entanglement to transfer information faster than light, But it's also impossible to tell what discoveries might happen in the future that might put this back on the table as a possibility. I hope you enjoyed this video, and I also want to thank my patrons on Patreon for supporting the channel. I really appreciate the support. I'll also remind you that if you'd like to join us on Discord for a more direct chat with me and more viewers of the channel that all enjoy science like you, see the description for the invite link. If you have any suggestions about science topics or recent science news that you'd like me to cover, don't hesitate to write it down in the comments. For more interesting science content, don't forget to subscribe to the channel and click the bell notification to be notified of all my uploads. You can also check out my website at respectyourintellect.com for all the information and videos on this channel. Until next time, thanks for watching, and remember, respect your intellect.